Hello, welcome to this lesson of our study of abstract algebra. Okay, so this is a brief introduction to abstract algebra. Okay, all right. So if you have not subscribed to the channel, kindly subscribe to support the channel as well. Okay, all right. So when you talk about abstract algebra, it's basically about two things. Okay, let me talk about them here. What you call group, okay, and rings. Okay, groups and rings. Okay. But in this particular lesson, we'll talk about groups. Okay, but before we talk about groups, let's go ahead and then take the step-by-step introduction to groups. Okay, so group is just how do you call it, some advancement of what you call some binary operation stuff that we know. Okay, already you know binary operation, but let's take a brief introduction to that, and then we'll just be okay with groups. Okay, now if A is a subset, I think binary operations. Okay, all right, let's do it like this. Now, but when we talk about binary operation, a binary operation on a non-empty or non-void set. Okay, so the set given should be a non-empty set. I mean set X. Okay, the binary operation on it is a function star. All right, from F, that is the function F, such that S star S belongs to S. Okay, so if A and B, if both A, B belongs to S, then we write, okay, here should be then we write A star B. Okay, what this whole statement here means is that the S star S belongs to star is that, let's say I have a binary operation defined on real numbers. Okay, numbers that belongs to real. Okay, it means that if I pick any real number and I cross it, or I start with another real number, I'll still get a value or a real number. That is what it means. Okay, that for whatever element you pick that belongs to the whole universal set. Okay, if we are talking about a set of complex numbers, the operation, let's say addition, will always be a complex number, or the operations, let's say multiplication, will always be a complex number. Remember that even if you have two is a complex number where the imaginary part is 0. Okay, I hope you understand. Okay, so the binary operation that we are talking about here, this star, okay, this star that we are talking about can be either plus, subtraction, or multiplication. Okay, division as well. Okay, so the binary operation doesn't necessarily mean a different operator. It means we can take any of these operators, combine them, and form some relation or some function for you, that for every A star B you pick, this is what it should be. Or something like A star B should always be equal, let's say, A minus 2AB, meaning the AB here means I have 2A times B. Okay, so I have minus and multiplication inside. Okay, so the binary operation is just, and it's like an identity or a function. That is why we mentioned a function in the definition. Okay, I hope you understand this. All right, let's talk about something that we call close under star. Okay, when do we say that a set, say A, is close under the operation star? Okay, so if A is a subset of the universal set capital S, then A is said to be closed under star if for every AB, so or for all, I hope you understand this. This is logical, or quantifiers. We call them quantifiers. Okay, for all, this means for all or for every. For all AB belonging to the set A star B also belongs to A. Okay, this is what I mean. Let's say if I have sets 3 and 0. Okay, then I pick let's say an operator like multiplication. Okay, let's say the operator you are talking about, A star B, here is equal to AB. So if I pick, this is A, so for every AB belonging to this A, and the elements in A are what, 0 and 3. Okay, we are saying every A star B is equal to A times B, meaning we are dealing with the multiplication identity or multiplication operator. Okay, so if I pick, let's say if I do it on a table form, This is my multiplication. This is 3 0 0 or 3 0 here again. 3 times 3, okay, will give me 9. 3 times 0 0 0 times 3. That's now you can see that for all a star b, all of them were inside a, because 0 is inside a, 0 is also inside, but 9 is not inside. So it means that this a here, this particular a we've picked here, is not closed under multiplication. That is why I said that the binary operation can be any of the operators you know, okay, or it can be a relation that consists of two of the operators combined together. Okay, I hope you understand. All right, so when you have all your results from your binary operation being part of the original set you are talking about, then it means you are talking about what the set is closed under the operation, okay, or the operator. Now, sorry, let's take an example and see. Let a be equal to that. Is a closed under, first of all, multiplication and addition? So the first one, a is what? 0 and 1, so 0 1 0 1 like that, okay. Now this is or should I use a straight line? Okay, let me try and use a straight line and see. Okay, let me actually clean everything and use a straight line for you. Okay, all right, so I have this and I have that. I have this as well. Okay, so with this I have multiplication for the first one. Okay, so I have 0 1 here and 0 1 here, so 0 times 0 like that, okay, and 1. So all the entries here, all the results that we had are these ones, okay. Are they inside a, or do they also belong to a? Because we said a is closed under the operator. When a star b here, the star is what? Multiplication, should belong to a for every two elements you pick from a. And whenever you pick two elements and multiply them, indeed the answer is inside a, because 0 is inside a and 1 is also inside a. The results are only 0 and 1, so it means a is actually closed under multiplication. Now let's look at addition and see. Okay, let's look at addition. Okay, so with the addition, you could see that this is addition 0 1 0 1. When you add this and this, 0 1 1 and 2. So all the results are what? 0 1 and 2. That's the result we had for the addition. And now since this 2 is not part of a, it means a is not closed under addition, because we said that for it to be closed under the operator, for whatever two values or whatever two elements in the a you pick and you operate them, the result should be part of a for us to get closure. Okay, I hope you understand. So let's move on to the next topic. Now let's d be equal to 2 4 6, where this means that is n, the d set is n such that n is even. Okay, is d closed under multiplication? So first of all, before you can tell if it is closed under multiplication, for every even number, okay, for every even number n, or for every even number, we call the even number what? Let's say we pick, for every first even number, we pick 2n, where n is a natural number. Okay, I hope you understand this. And the second one will be what? 2n plus 2, okay, where n is a natural number. So if let's say I have a natural number, let's say 1, okay, when n is starting from 1, okay, when n starts from 1, let's say n is starting from 1, first element will be 2 times 1, which will be 2. The second element will be 2 times 1, which is 2 plus 2, okay, and that will be 4. The third element will be 2 times, what do you call it, the second, I'm coming, the third one will be 2n plus 4 or something like that. Okay, I hope you get it. Or you can also say that it is equal to n plus 2, where n starts from 2 or whatever. Okay, but I hope you can see that this is the same as 2n and 2n plus 2. Okay, I hope it's okay now. All right, so or you can actually say it is 2n plus 2, where n start from 0. Okay, and it means you'll be getting an even number as well. Okay, depending on how you define it. Now let's talk about multiplication. Okay, so I have this. Let me see. You are saying that this 2n is an even number. Okay, I mean 2 times any number is an even number. You can try that and see. Okay, so I have 2n for every 2 even numbers. This is how they are, either 2n where n starts from 1 and 2n plus 2. That is from the first one to the next one. This is how it works. Okay, so like I said, you can even use it to generate the rest of the terms. Okay, this actually, the next one should be 2n plus 4. Okay, and you can see that the difference between these is just if I subtract them, it's just 2. Okay, and the next one is 2n plus 6, like that. It goes like that. So if I pick the first two, okay, the first two, if I pick the first two, then I multiply them. Okay, 2n plus 2, and try to see. Okay, if you try to see, you could see that 2 will be, or let's try to multiply them and actually talk about what I'm trying to say here. So we get 4n squared, okay, plus 4n. I hope you can see this, what I'm going to. Okay, I hope you can see what I'm going to. And for let me see. My bad. I'm really sorry for that. Okay, we can actually use a different method, but let me finish with this. Okay, let me finish with this one so that I will use the other method as well for you to also know. Okay, so for this, if you get this, if you define this like that, and this will be equal to what? If I want to factor 2 out, okay, I can get 2 into 2n squared plus 2n. Okay, and you can see that this is 2 times something. Okay, and I said 2 times any number is an even number, provided, and we said n is actually a natural number. So if I have n is 1 and I'm getting like 2 times 1 squared plus 2 times 1, I'll get 2 multiplying the whole of the bracket, and that will be still an even number. Okay, 2 times any odd number is an even number. 2 times a prime number is an even number. 2 times any number is an even number. So it means that indeed this is also an even number. And since we had an even number for multiplication, it means the operator, this set, how do you call this set D, where the operator here is what? Multiplication. This set D is closed under multiplication. Or you could see that we let an element P belong to D, where we define P to be equal to 2n, where n is an even a natural number, and let's say Q is also belonging to D, where Q is also equal to 2m, where this m is also a natural number, but they're not the same as n. Okay, I mean, since when you multiply 2 by any number, you get an even number, we can define them just like that, that P is 2n and Q is also 2m. Okay, with that, it means that for the multiplication, I'm doing it again. I have 2n by or times 2m. Okay, and this will give me 4nm. And if I want to factor 2 out, I'll get 2 into 2nm. And this whole thing is 2 times something. That will give me an even number. Okay, it depends on how you want to do your even number. Okay, so it means the operator, the set D, where n is an even number, is closed under multiplication. Let's try with addition and see. Okay, then you move to the next subtopic. Okay, with the addition, let's use the P and Q, okay? So I have 2n plus 2m. For all of them, this is how you can define them. If I factor 2 out, I have n plus m. And since I have 2 times something, indeed, this belongs to D because it will be an even number. So it means that the set D is close under multiplication and close under addition as well, okay? I hope this is okay. All right, let's move on to the next one. The next subtopic is associativity. We are going through all these because we use these to define group, okay? An operation star on a set so an operation star on a set S is associative if for any elements A, B, C belonging to S, we have, first of all, operate A and B first in one bracket, then you operate it on C, then you operate B and C first in another bracket, and you operate them upon A, okay? I hope you can see this. So this is one of the other things we should know, okay? One of the properties you should know. I hope it's okay now. Now let's go to an example. The question is, determine if the following operations on the set of integers are associative, okay? So if you have two integers, let's say addition, okay? Let's say I pick two integers, how do I call it? Three of them, n, and let's say p. Let me pick p. Let me see, n plus m plus p, and m plus n plus p. Are they the same? Because this is the same as n plus this, okay? And this is the same as m plus n plus p. So it means since they are the same, because addition is just like that. No matter how you put the bracket, they are still addition, okay? Since it is addition, it's addition. And since this is the same, it means the operator or the set Z is actually associative under addition, okay? I mean the set of integers, okay? So you just check like that. Sometimes you can be given some finite example. These are infinite examples. So this is true. Sorry, for addition, this is true. Let's go to subtraction and see. Now I have m minus n minus p, okay? Now let's go to m minus, look at this, n minus p, okay? Now with the first one, let me actually bring this one here so that you understand the first one. This m minus n minus p. Now with the first one is the same as this. Let me use another pen. The same as m minus n minus p, and nothing changes. Now with the second one, the same as m minus n plus p, and this is not equal to this. So it means subtraction, the set Z is not associative under subtraction. I hope you can see what I'm trying to do here. I'm trying to fish out some properties here, and then we are using examples to understand the properties, okay? Sometimes you'll be giving just infinite examples like this, so stay cool and just work, just look at it, okay? With the multiplication, m times, let me do this first, m times n times p, okay? I'm using this as multiplication. This is the same as m n p, just like that. And m times np, this is the same as m n p, and they are the same. So it means this is also associative under multiplication. The set of integers is associative under multiplication. I hope you understand. Now let's move on to the next subtopic. Identity. An element E in S is called an identity element for an operation star on a set S if A star E equals E star A and is the same as A. So for all A in S, okay? So this is very important for all A in S. So if I say 1, 0, let's say 2 or negative 2 belongs to some set, let's say A, okay? And I pick 1 and I say I operate it on 0 and I get 1 again, okay, and I pick, let's say, -2 and I operate it on 0 and I get -2 again, then it means that this 0 is the identity, because whatever element I pick and I operate it on, I'm getting the element back, okay. That's what we mean by the identity, okay. All right, so let's go to the next one. We have inverse. The inverse on an element A in S is such that A star A inverse equals A inverse star A, and it's the same as the identity element E, where A inverse is the inverse of A, okay, and E is the identity element, okay. I hope you understand. Now, let's say with the example I gave, I have these elements as 1, 0, -2, okay. Now, you know that the identity element is 0. That is, let's assume that is the identity element, okay. Now, if I pick 1 and I operate it on -2 and I'm getting the identity element back 0, it means I've not defined any operator, so we are just assuming that whenever you pick 1 and you operate it on -2, you get 0. It means that 1, the inverse of 1 is 1 inverse, okay, the inverse of 1 is equal to -2. And vice versa, because if you operate, when this happens, you operate -2 with 1, you get the identity element again. So it means if I also operate this, okay, with 1 and I'm getting 0, it means that the inverse of -2 is also 1. I hope you understand this. So that is what we mean by the inverse. Now let's look at some terms here. Magma. Okay, a set equipped with a binary operation star is said to be just magma, okay. So you can see that a normal binary operation, or in a normal set under a binary, or defined under a binary operation, is called a magma, okay. All right, let's move on to the next one. Groupoid, a set equipped with a binary operation and also closed under star. So you can see that we are using some terms to define them here. So here there's a binary operation, or the set is defined under a binary operation, and the set is also closed under that operator or that binary operation, okay. And go to semigroup. Now, semigroup is a set equipped with a binary operation, closed, and also associativity. Okay, there is an associativity here. You have the set, which is defined under binary operation star. The set is also closed and associative again. I hope you understand this. Now let's move on to the next one. Monoid. A monoid is a set equipped with a binary operation, closed, okay, associativity, and has an identity E. So monoid is just a set defined under or defined by binary operation, and the set is closed under that, is associative, and has an identity element. That's what we call monoid. Now let's go to the main topic for the day, what we call the group. Let G be a non-empty set. The set G equipped with operation star, okay, so here there's a binary operation here, is called a group if it satisfies the following. First of all, if the set defined under star is closed under star, okay. When I say closed under star, I hope you understand. That's why we went through the closure and those stuff. It's closed under star. If the set is associative under star, if there's an identity element under star, under this operator star, okay. And also if there's an inverse for every one of the elements in G, okay. Remember, G shouldn't be an empty set. It should be a non-empty set, okay. I hope you understand now. So for all the subtopics we discussed, when they are present, then we are talking about group, close, associativity, identity element, and inverse, okay. Now let's move on to some term here. A group that satisfies the commutative property or commutative property is called abelian group. In the commutative property, you know that A star B is the same as B star A. B star A. That's what we call commutative property. A group that continues after obeying or satisfying the axioms I listed just recently or just previously. These axioms, if the group satisfies them clearly and also continue to satisfy this commutative law, then it means the group is called abelian group. Okay, now examples, let's look at some example. We will check if this is group and also if it is abelian or not. Okay, now what this means is that this is the set we are talking about. This is the operator. Okay, so the binary operator here is addition, and the set is what the set of integers. Now, is it close? Yes, for every numbers or every two numbers you pick in the integers, the addition will still be in an integer. Okay, this is perfect. This is cool. Okay, I hope you understand, because if I pick 2 and 3, if I add them, I'll get 5. Okay, if I pick -1 plus 0, I'll get -1, which is also still what do you call it, an integer. Okay, so this is the first point here. Okay, the first point here, which is closure is defined here. Okay, so you go to associativity. Okay, associativity, what is associativity we are talking about? When I pick 2 plus 3 plus 5, what will be the final answer? It will be 5 plus 5, which will be 10. Okay, and 2 plus 3 plus 5, this will be 2 plus 8, and that will be 10. Okay, in other words, if I pick m n p belonging to z, m plus n plus p is the same as m plus n plus p, because when you remove the bracket, they will be the same. Okay, I hope this is okay. So this is indeed associativity is also cool here, and you are good to go. So the second point, which is associative, okay, associativity or associative is also defined here. So we are left with two more properties to define to determine if this is a group or not. Okay, so we consider, how do you call the next one is identity element. Okay, so you ask yourself, what element within the z? Okay, so you can go back to the z and see this z, you could see that in the middle we have 0, because 0, then -1 here, then let's say 1 here. For set of integers, this is how the integers are. Okay, then you are going to this way. So since we have the 0 there, let's try to add every element to 0 and see, because we said that for the identity element, whenever you add something to it, you get the same thing back. Let's say I pick 1, I add it to 0, I'll get 1. I pick -1, I add it to 0, I'll get -1. I pick 20, I add it to 0, I'll get 20. I pick -25, I add it to 0, I'll get -25. So it means that the identity element here is what? 0. Because for every element you pick and add them, you get the same, you add it to 0, you get the same element back. Okay, so with the identity parts, okay, with the identity parts, it's also satisfied here. And you go to inverse. Now, is there any element that when I add it to, let's say 1, I'll get my identity element? Yes. When I add 1 to -1, I'll get 0. When I pick 20 and I add it to -20, I'll get 0. When I pick -50 and I add it to 50, I'll get 0. So it means for all of the elements, all of them have their individual inverses, where when you add them to them, you get back your identity element. So it means the inverse is also satisfied, the inverse part. Okay, now the question is it abelian or not? Okay, this is group. Indeed, all of these are satisfied. So is it group? Yes, it's group. Is it abelian or not? It's abelian, just because when I pick 2 plus 5 is the same as 5 plus 2. When I pick -2 plus 3 is the same as 3 plus -2. Yes, this is also abelian as well. Okay, now this Q star means all the rational numbers with how do you call it, 0 excluded. Okay, so 0 is not part, and since 0 is not part, with their denominator is not equal to 0. Okay, I hope you understand this. That is a Q star with multiplication. So if I pick, let's say, A over B, and I multiply them with, let's say, C over D, I'll get AC over BD, which where this will still give me a fraction, and that is how do you call it, a rational number. Even if I get something like 2 at the end, is 2 over 1. Okay, so this is also a rational number. Okay, so for every multiplication you have a rational number, at the end. Okay, so it means closure is defined here. Okay, with associativity, yes, indeed, it's also defined because A over B multiplying C over D, or multiplying, let's say, E over F is the same as ACE over BDF. And if I do it like this, A over B times C over D multiplying E over F, the same thing, ACE BDF. I hope you understand this. So with associativity, this is also true. Okay, so we are done with the first two. Now you can go ahead and try for the identity elements. With identity element is 1. The identity element here is 1 because for every element, or for every element you pick in the rational numbers with 0 excluded, when you multiply them with 1, you get the same element. And for the inverses, for A over B particularly, its inverse is B over A, which will give you the 1 back. Okay, so it means that indeed this is also a group, so you can go ahead and check if it is abelian or not. So you can also check with this one and then see. So with this one, it means that this here means a matrix with m by n, okay, m by n dimension with s entries under the operation addition, where s can be integers, rational numbers, real numbers, and complex numbers, and the operator is what? Addition. And this is a group, so you can go ahead and verify this for your own self and see if it is correct. Okay, so for you to be able to know that a particular set given is a group, okay, with an operator is a group, check for what we call kin. Okay, I hope you understand what I'm coming to write the full meaning for you. Check for kin. Okay, kin. This C means closure. Okay, closure. Check if the set is closed under the operator. This means how do you call it? Is it let me see. Associativity. Sorry, I forgot. Okay, associativity. Okay, associative, let me put it that way. And the I is what we call the inverse, identity. Okay, identity. And this N, the last one, does not necessarily how do you call it, sound good here, but it's called the inverse. Or you can also come up with your own abbreviation, something like this kin, but with this one, it becomes something else, where this will be closure, associativity, identity, and this whole thing will be inverse. This can also work for you. Okay, all right, so thank you, and don't forget to subscribe to my channel. In our next discussion, we'll talk about picking some terms associated with groups, like order of a group, some particular types of groups, and so on. Okay, see you next time.